Hello, everyone. Just trying to log into for the online students. Um, all right. So we're going to switch gears today and do something else. So we were looking at x86. And all right. So once again, the big picture, we are looking at the first 6 weeks, at least, processor, main memory, and storage. We looked at x86, and it will be helpful for you to understand some of the trade-offs, how system calls are made. There's so much to do for one lecture. All right, so I want to give you our plan for what are we going to do the next few weeks. These are really important weeks for the lab assignments and for what we are going to cover in this course. So the question, we are looking at CPU first. The question is, we have many programs running on a single processor. So forget about multi-core processors where each processor has a different core. Think of a single processor, single core. You have one program counter, one set of ALU and all that. So one CPU, many programs. How do we give programs the illusion that there are instead a number of so-called virtual CPUs? How do programs share these CPU? And we call this virtualizing the CPU. We have a single processor, single CPU, yet today there are hundreds and thousands of programs that may be running or sleeping or waiting to run on a single processor. How do we create this illusion that there are many, many processors and there's a lot of things going on at the same time? The key theme we need in here is the abstraction of a process. Process, as we will see, is not the processor or the program. Instead, it is a program in execution. When we run a program that is stored on a disk as an executable binary, when we give it life, when we give it a spirit, it becomes a process. And that is a key abstraction we need to learn here. Similarly, you can see in the previous diagram that we have only one physical address space. If we have a 32-bit system, we have a 4 GB address space. If we have a 64-bit system, we have many terabyte big address space, but it is a single physical address space. And yet we have many users sharing a program, a computer. We have many, many programs running on a computer at the same time. We need to virtualize this resource. We need to give these programs the illusion that they have the entire address space, the entire physical memory to themselves. Now, obviously, it's not physically possible. You need some way to share. It's a single resource, a single address space. How we do this, we call it virtualizing memory. We have physical memory as a single resource, and we are going to virtualize it and share it among different users or different programs such as Spotify, WhatsApp, Word, Gmail. All of these programs have this illusion that they are the only one running on a system. They have the full ownership of the address space, the CPU. And what is the third thing that is really critical in a computer? I/O devices, specifically, we are going to focus a lot on storage. We don't really create a private virtualized disk for every program, as we do for CPU and memory. We don't create an illusion that each program has the entire hard disk or storage device for themselves. The intuition is that programs share files, and we need to facilitate that sharing, that management. And the way we do that is through a file system, a data structure that helps us organize whatever we want to store on a disk or a storage device in a proper way. So we can easily find the information we need. And we will try to understand file I/O, file input output, and how programs read files from file system, write files to a file system, and all that. So the big picture is we need to understand how a computer is shared, how the key components, CPU and memory, are shared by different programs. Okay, if we look at a processor at any given point in time, it will appear as if it has a single control flow, a single physical control flow from startup to shutdown, from the point we start a computer to the point we shut it down. If we look at the values that the program counter takes, all we see is a sequence of instructions, and the processor executes those instructions one at a time. And we call this the control flow of the processor, the physical control flow. We have looked at two mechanisms that can change the control flow. And the two mechanisms are jumps and branches and call and return instructions. When we make function calls, when we have jumps and branches, we change the control flow of the processor. So instead of executing instructions one after the other, it jumps to an instruction that is not the next instruction. It goes somewhere else. And these are reactions to changes in the program state or program variables. This is insufficient for useful systems. A processor or a computer needs to react to changes in state that are outside the program. And some examples are okay, I think this is too much for one lecture. Like, how many things have to set up? Honestly, there should be something. All right, so what I was saying, you need to react to changes. For instance, you have signal coming from an environment. It could be anything. It could be data arriving from the network, and you might need to respond to that. It would be you're pressing Control-C from the keyboard, or you're sending any other signal to the program. We will look at signals later on. These are events that change the flow of a program. Or if you have a divide by zero exception, you need to change the flow of the program or the processor and go somewhere else. And we call this exceptional control flow, reacting to changes not captured by the internal program variables. Now, the thing is, once we understand how exceptional control flow works, exceptional here means that this is a change in the control flow that is not due to a change in the internal program state. Something has happened outside the program. Once we understand how exceptional control flow works, we will be able to understand how a computer or processor CPU is shared by different programs. We will build upon this for those abstractions that help us share the processor. Okay. So exceptions, where we respond to a system event. And one of the key things we want to understand is how exceptions are implemented. Who does what in terms of what does the CPU do? What does the hardware do? And what does the operating system do? The division of labor to make exceptions work. And then exceptions also appear elsewhere. You might have written Java programs where you throw an exception if something happens, a try, catch blocks in C++, signals that we will look at where you send a message to a program that is running to get its attention to do something for you. And most importantly, the context switch. What it means is when you move from one program to a different program running on the same processor, we call it the context switch. We will look at that. So exceptional control flow is everywhere. Let's start with exceptions. So an exception is a transfer of control to the operating system kernel in response to some event that the processor detects. Now, it could be that the processor has a special pin and an input-output device, a disk, or any other input-output device sends a signal on that pin, and the processor goes, oh my God, I need to do something. I need to do something else. I need to stop doing what I am. Typically, I would execute, this is the processor speaking, this is not me. Typically, I would execute the next instruction, PC plus 4, but hey, there's someone needs my attention. Let me go somewhere else and do something. Let me handle that exception. It's an example of an exception. So kernel, once again, kernel here is part of the operating system that actually manages the hardware. We call it the kernel, and operating system is this huge, big thing with graphical user interfaces, GUIs, and shell, terminal, and a bunch of other things. Kernel is the core component of the operating system. It's always memory resident, and it's the one that is very tied to the actual hardware devices. It's managing all those resources. And so an operating system is with all the, things around that kernel. So imagine that you are executing, the processor is executing instructions in user mode. There are two modes that an application could be at any given point, the kernel mode and the user mode. In kernel mode, the kernel code, when the processor is in kernel mode, the code that is executing could include very special privileged instructions that can do very low-level things. In user code, user mode, the type of instructions, applications, or the code can execute are very restricted. So you don't mess up the system for everyone. Okay, imagine that you are running, the processor is running a user code, and an event takes place. This could be any event. This could be, as we were saying, someone needs attention, an I/O device, an input-output device. There's an exception. You somehow, and we will look at the mechanism, somehow you enter the kernel. So you can think of the application in terms of layers. There's application running on top of the operating system, and then kernel is part of the operating system. So somehow we leave the domain of application code, whatever code the programmer has written, and we enter the kernel code. The processor then executes instructions in the exception handler. Each type of exception has a corresponding handler. Once the processor is done executing the code in the handler, it could return to the same instruction and re-execute that instruction. It could execute the next instruction, or it could simply abort. A lot of operating systems, when there is divide by zero error, they just abort the application. Others handle it more gracefully, and they re-execute the instruction. So depending on the scenario, you may or may not return back to the same instruction. And then you execute the instructions in the control flow of the program. Okay, so how does the CPU know what code to execute? Where is the exception handler for a specific type of exception? So what we are going to do here is very similar to the jump table that we did for switch statements. Each exception in the system, or each exception that can happen, has a specific number. Some of these numbers are decided by the processor manufacturers, and others are by whoever writes the operating system. So we have an exception table here, same idea that we had in the jump table. We have an exception table, and we have a bunch of pointers that are stored. And these pointers are addresses of the code blocks or the code for the different exception handlers. So whenever you have an exception with a specific number, 0, you index into the exception table, and you go to the exception handler and start executing the code for the specific handler. All right, this looks like a jump table, right? That we looked at in the implementation of the switch statement. You store the code for the handlers somewhere in memory, and the starting address of each handler is stored as an array in this exception table. You look at the exception number, and you index into the table, and you go to the handler and start executing the code. Okay, so there is typically an exception-based register in the CPU that stores the starting address of this table, the base address. And then you add it. So what are you adding here? Meanwhile, I try to get the chat on. What are you adding to the base register, contents of the base register? All right, I now have the chat. Good. So we're taking the exception number and we are multiplying it by 8. Why are we doing that? Because each pointer, each address is 8 bytes. Same idea. You take the exception number. For each type of event, whether it's someone raising a signal on a CPU's pin or divide by 0 or any kind of event, the CPU knows the exception number. If it knows the exception number and it knows the base address of the exception table, then it can reach the address of the exception handler. All right? So we can see that there is a clear division of labor between what the processor is doing and what the operating system is doing. The processor has the base register. It detects the exception number depending on the type of event, and then it executes an indirect procedure call to the handler. We need extra hardware here to support all that. We need an extra register. We need some logic. And then the operating system actually executes the exception handler. When the exception handler is running, the CPU enters kernel mode. It can execute privileged instructions. And there are a few extra things that the operating system do. So it's pretty much like a function call, except that we push some extra stuff on the stack, and there is a special return from interrupt. This is a special type of return for supporting returning from an interrupt or an exception handler. And then you restore the state to user mode, so the user mode application can start running instructions in the program. Interrupts are caused by events that are external to the processor. So we have different types of exceptions now. This was the basic idea, the general idea of exceptions. We have different types of exceptions. One of them is interrupts. Interrupts mean that there is an event that is external to the processor. This could be, as I was saying, something happens on the processor's interrupt pin. There's a special pin on the package, the processor, and input-output devices can raise a signal on that pin, just like people are raising hands here with a Zoom, you know. And someone raises a hand and says, I don't want to annoy you, but I have something useful for you to say, to say to you. Handler returns to the next instruction. When the handler is done, you know, whatever the input output device wants the processor to do, you execute the next instruction. An example is a timer interrupt. There are timers that every few milliseconds, there's an external chip that triggers an interrupt in different systems, embedded systems, CPUs, for other type of environments. And interrupts from external devices. When you press Control-C at the keyboard, when you're running a program at the terminal, you notice that something happens. The shell kills the program. A packet arrives from the network, or data comes back from disk. These are all examples of interrupts. So these are asynchronous exceptions. The program is doing something, and all of a sudden, an event takes place that is completely outside the control of the program or the processor. Now, there are synchronous exceptions that are caused by events that occur as a result of executing an instruction. You actually execute an instruction to generate an exception, okay? Examples are traps. These are intentional, and we are soon going to look at how traps are used to implement system calls in our systems, breakpoint traps, special instructions. So whenever you have a trap, you return control to the next instruction. Faults are also synchronous exceptions, page faults, protection faults, floating point exceptions. A lot of you are seeing a special kind of fault in the labs. What is it called? What's the name of it? Segmentation fault. Okay, so hopefully after 1 or 2 lectures, you'll understand what that means. It's an example of a synchronous exception. You try to do something, you do malloc, memory allocate, you do something wrong, you allocate 4 bytes, and you try to access a random byte somewhere in memory, and the processor doesn't know what to do. So it won't let you just randomly access anything in memory. So it generates a fault. there is no point in returning to the next instruction. It's a correct program at this point. You have corrected the program, your environment. So the processor or the operating system cannot go to the next instruction until you fix your program, until you fix your bug. So fault, there are other types of faults. Just start becoming familiar with these words, but I'm going to explain them in detail. Page faults, protection faults, memory protection faults. Abort is unintentional and unrecoverable illegal instruction. Something hits the processor, it's damaged, beta particle, stuff like that. You simply abort the program. So faults and aborts are aborts, you always abort, and in faults, you could try to re-execute the faulting instruction. So we call it the faulting instruction. When you write malloc, the compiler will generate some assembly, and at some point, you will do something critical that actually generates the segmentation fault, and we call that the faulting instruction. Okay, so bottom line, interrupts are asynchronous exceptions. Something happens that is outside the control of the processor or the program. Something happens in the environment in which the processor or the program is running. Synchronous exceptions are caused by when you execute an instruction. And the instruction that we are going to look at is syscall. And this is used to implement system calls in today's systems. So system calls are, examples are, so what is a system call? You want some service from the operating system that requires the interaction with low-level hardware resources. And we don't let applications randomly access those resources, because if there's a bug, if there's a problem in the program, it will create problems for everybody. The type of system calls that we have, so from your user program, the applications that you're writing in labs, you make system calls to get some service from the operating system. Examples of those services are reading a file, reading something from a file, writing something to a file, opening a file, closing a file, getting some information about the contents of the file. Here, stat fork is used to, when a program is running and it needs to create a new instance of itself or of a different program, we use the fork system call. Kill, exit. So you will see these names, and you can use the name of the system call from your user program to get some service. So system calls give a procedure like, it looks like an ordinary function call, but the difference is that you are entering the kernel code, you are entering the operating system, and the operating system will do something for you. There is a special instruction to support system calls. So this is support in the instruction set architecture. So system calls are supported by the ISA. We say that ISA has special support for system calls. So syscall is an instruction that you can use to make system calls. And N is the identifier for the type of system call you want to make: read, write, open, close, stat, fork. So the way system calls are implemented is whenever you have a syscall instruction, there's a trap to an exception handler. The same way, the same thing we looked at, there's an exception table in one of the slides a while ago, where you look at the exception number and you go to the handler. Similarly, there's a table that stores the addresses of the code you want to execute for each system call. Trap handler decodes the arguments and calls, the appropriate routine, and the system call, importantly, runs in kernel mode. It can execute privileged instructions that the user application cannot, and it uses a stack that is defined inside the kernel. All right, let's look at an example. So you're writing your program. So you don't do that normally. There is better abstraction for making system calls in C, but we're just looking at an example how it looks like in assembly. The system call ID number you want to execute, you move it to EAX register, and then you simply execute the syscall instruction. And the rest of the work is done by the processor when it sees the syscall instruction. So whenever there is a syscall instruction, it's treated like an exception. You do the work that the system call wants to do, and then you return control to the next instruction. So what is the next instruction here? After the syscall. So RAX contains the syscall number. The syscall arguments are passed in these registers. The return value is in RAX, and negative value is an error corresponding to negative error number. We'll look at in a bit what error number is. So whatever the syscall returns in RAX, we need to compare it to a negative value, and it's system dependent. Here, it's comparing it to -4095, that's Linux. And if the value is between, if the return value is between -1 and -4095, it means there is an error. So the assembly code here is checking if the syscall handler did something that resulted in an error. But system calls are really easy to make. You need to know which system call you want to make. You get the number, you copy it in EAX and system call, and what you get in return is something in RAX. And they look like exceptions. So here you are comparing, and you can have to handle the error. So in this example here, we are not doing anything to handle the error, but you could actually jump somewhere, and this label means handle the error. Okay, this is a more gentle way of looking at the assembly code. This one is actually disassembled using obj dump. Okay. So system calls that we will use starting next lab. By the way, next lab will be very lightweight. I know that lab 3 is a little bit too much work. So you have 2 labs to finish lab 3 almost. we will start using system calls in future labs. Okay, let me return to this later. These are examples of if you have an okay, let me return to this later because we don't know what page for this yet. So I want to start looking at processes. A process, as I was saying, is an instance of a running program. Once again, when we compile our C code, the resulting binary object or the resulting binary executable is stored on a device, a disk, or on your laptop, on a solid-state drive, and it has no life. It's really dead. It's not doing anything. It's just laying there. When we give this binary executable some life spirit, it becomes a process. So a process is an executable that is actually running. Anything that has life spirit, like living beings, what are the things they need? What do we need to survive? Air, shelter, food, mobile phone, lots of money, and Tesla, and job, and oh, the wish list is really long. But we can call all these things. What is the keyword? What can we call these things? Resources. So a process in a program in execution needs resources, right? So unlike human beings with very big wish list, what kind of resources do processes need? CPU, memory, storage. But the problem is there's a lot of processes running on a system. And they all have this desire that they want the CPU for themselves, and they want the memory address space to themselves. So let's see how we do that. A process provides each program with two key abstractions. We cannot provide each process the full physical CPU and the full physical memory. That would be cheating. That would be a very bad scheme because we know that we only have one processor. What we could do is the first slide where I showed you the control flow, a sequence of program counter values was a physical control flow. I was actually monitoring what is happening inside the processor. What we could do is we could provide a logical control flow, meaning each program seems to have the exclusive use of the CPU, but from time to time, we switch to a different process. If we have two processes, we give a slice of the CPU to one process, and after a few milliseconds, we give the CPU to a different process. This is called time slicing or multitasking. And this is enabled, logical control flows are enabled by a kernel mechanism called context switching. We switch context, you can think of, it's a term from linguistics, but you can think of context as environment. What are the specific, what is part of the context of, what could be part of a process context? What are the things that are really tied to a process that are part of the CPU? The program counter, the register file, and all of that. That is the context of a process. Now, the contents of the memory that belong to the process, the open files that the process is using, all those things are part of the context of a specific process. As long as we can safely save the context and restore it, we have a mechanism to switch between multiple processes. So context switch enables logical control flows. Stack, heap, data code, CPU registers as long. All right, sorry. So process provides each program with two key abstractions. One of them is the logical control flow that is related to the CPU. And the second one is the private address space, and that is related to RAM. A private address space is really important. We only have one physical memory, and somehow we have to give the program the illusion that you have the entire address space to yourself. And this is enabled by a key mechanism I was saying before, virtual memory. We are virtualizing these resources like virtual reality. I don't really have an address space, private address space for 1,000 processes or 1,000 users, but enter virtual reality, I'm going to create that illusion. All right, so at any given point, we need to create this illusion, given that we only have one processor. This is a snapshot of my laptop a few hours ago, and there are about 546 processes. I don't know what they're doing. I was just listening to music and preparing the lecture slides. So two are running, and the rest are sleeping, waiting for something. Demons, you know, the operating systems today, they use a bunch of processes just to manage right here, Spotify and all that. Okay. Each process has a process ID, PID. So if you do top on your laptop, on any machine, which is Unix-like, you open a terminal, open a shell, you do top, you will see the processes that are running, and on the very left, you have the process ID. Okay. So we have the context, stack, heap, data, code, save, registers, but we only have one physical CPU. So what we do is we save the current registers, we save the context in memory somewhere, and we move to a different process. We start executing that process, and then we switch back to the, okay, so the key idea here is, this process is called scheduling. What we are doing is we have all these different contexts stored in memory, and we can move between those contexts with a scheduling policy and give each process the illusion that it is the only one running on a system. Now, in reality, the process may be waiting for the next instruction to execute. But we can create we can still create that illusion. Okay. So here we are restoring the CPU registers. We typically don't need to restore the contents of memory. They are stored there. They are not overwritten. So whatever saved registers we have in memory, we restore them and we start running process B, and then we move here and start running process A. As long as we can safely store the registers somewhere and restore them, we can context switch between these different processes. Today, most machines have multi-core processors, and different contexts, different processes are actually running on different cores or different processors. So as I said in the first lecture slide, concurrency is when you have two processes that may be running at the same time, but you only have one resource. So you only have one CPU. and you have two processes, A and B, that are time sharing. This is an example of concurrency. Parallelism is when you have two separate CPUs and process A and process B at the same time, they are running on two different physical resources. So a distinction between parallelism and concurrency. Concurrency and parallelism both are important today. Okay. Concurrent processes, each process is a logical control flow. We already know that. If we have 10 processes that are mapped to the same physical CPU, we have 10 logical control flows, and we have one physical control flow. Let's do an example here. These are three processes that are running on a single processor computer, single CPU. Process A and B, do you believe they are running concurrently? No, no, wrong. Look, concurrency is, regardless of the actual resources, if two things are happening at the same time. This is time on the vertical axis, okay? When process B is doing something, is process A still live? Is it still active? It's been switched out, it's been scheduled out, but it hasn't terminated. So if you look at in time, the process A here, okay, I should do there, sorry, the online students. The process A at this point is still doing something. It hasn't exited, it hasn't terminated. When you write the main function, what terminates the program? Return, right? It hasn't returned. It just doesn't have the resources. So the operating system has scheduled it out, saved its context somewhere in memory, the registers and everything, and the operating system is running process B because it would be unfair to not run a different process from time to time, okay? So if we look at this window of time, we see that although process A and process B are not running at the same time on the same physical resource, because we only have one physical resource, they are active in that window at the same time. And so A and B are running concurrently. What about A and C? What about B and C? B and C? Their execution does not overlap. They're disjoint in time. Okay? So this is an example of three logical control flows running on a single CPU. So we have a physical control flow here that belongs to three logical control flows. So if we look at the physical control flow, we may or may not be able to tell which process is running at a given point. So processes are managed by the kernel, which is always resident in memory. It's a core component of the operating system. The kernel is not a separate process, but it actually runs as part of the existing process. When processes make system calls, you start running the kernel code, and you come back and start running the user code. Yeah. So B terminates here, and C starts here, and B never runs again. Their execution never overlaps in time. So the way control flow passes from one process to another, process A, when the kernel decides to schedule it out, there is some code that runs in the context of process A, and then the kernel brings process B, it runs process B for a while, and then the control switches back to process A. This is a simple illustration, how you go back and forth between user code and kernel code on a context switch. All right, so now how can we create processes? Now let's turn our attention to programming. So one important thing when we write system programs that make use of system calls is system level functions. Okay, what is a system level function? You never actually write assembly to make system calls. The work is done for you by the C library. So the C library actually has a corresponding to each system call that you can make in assembly. It actually has a high level function with the same name. So to avoid any confusion, we call them system level functions. And you can call them, you can call it system call or system level function. It's the same thing. You just need to know that these functions are actually doing the low level work. Whenever something goes wrong, system level functions or system calls return -1 and set a global variable error number to indicate the cause. It is a good practice whenever you're writing system, whenever you're using system level functions, making system calls to handle the error and check for the error. So here, we will soon find out what fork does. This is the process ID. So we are calling fork, and we are, whatever is returned by fork, we are storing it in the variable PID, and we are checking if it is less than 0, what happened. And this printf statement here is actually writing to standard error. Have you seen standard std out, std in by now? So there are 3 files that are associated with every program on Linux or Unix-like operating system. Standard input, standard output, standard error. Standard input is for giving input from the keyboard. Standard output is for printing things on the screen. And there is also standard error where some programs decouple the standard output from the error errors that appear from the program. So here we are writing to standard error. There is an error when the system call was made, and this is a function's std error that actually turns the error number into a fancy string. Okay, so this is a good practice that we would like you to follow. Whenever you make system calls, check for the return value, and if it's less than 0, exit right away. Don't move any further. Something has gone terribly wrong. We can have a wrapper for those 1, 2, 3 lines. So here we have a Unix error function, which you pass a message, and internally it does the fprintf and exit. This is just showing that you can actually shrink the code by using this function. Actually, you can shrink it even further. The the header files and the code the book provides, and we will provide it to you, actually uses this convention. You have a system call starting with capital letter, the name of the system call, and inside they do a bunch of work for you, checking error, generating error, and all that. So you, in the end, are left with a single, very concise statement. Okay, this will come up again in the labs. You can get the process ID for a process when the process is running. If it calls get PID, you will get the process ID, and you can get the process ID of the parent process. Now, I think it's important before we actually look at an example, but the example is a bit far away. Okay, so these are utility functions for getting each process has a parent and processes have children, and we will learn how we create child processes, how we deal with parent processes a little bit differently than we deal with in real life. But you can get the process IDs using these calls. A process could be in 3 states: running, stopped, or terminated. Stopped or suspended is when, for instance, the operating system decides to run a different process. The running state is when the process is actually executing instructions, and terminated is the process is stopped permanently. It's not consuming any resources. The process can also terminate by calling exit, or we can send a signal to terminate the process. So you can think of signals as when you type Control-C from the terminal. Have you ever terminated a program from the terminal by typing Control-C? You type Control-C or Control-Z or Control-D on different, depending on the operating system you can terminate a process. We will see examples of all this. So how does a parent process creates a child process? And the system call, the first system call in detail that you're going to look at is fork. Fork actually creates a child process. It's an interesting system call, very confusing. It is called once, but returns twice. It creates a new child process with a private address space and a logical control flow. The child process gets 0, and the parent process gets the ID of the child. Okay, let's look at an example. So here, this is a main program. So whenever you double click on your desktop to run an application, and when in terminal you type the name of a binary you want to run, this is what is happening behind the hood. So this is what we're looking at. So you can write applications now that do those things, that help people run applications, binary executables. I have a variable x equals 1. This is a special type. You need to include a special file for this, process ID. So I'm using this variable, and I make the function called fork using the very elegant syntax I showed you, and stored the output in PID. Now, what's happening here is, at this point, both the child and the parent process are now running. So the fork system call has created a new child process that inherits the environment of the parent, the open files, the address space, and they both start executing this code. So what is this doing? whenever you call fork, it returns 0 in child and process ID of child to parent. The if statement is checking what? What is the if statement trying to do? It's trying to tell the parent, stay away. So when the parent executes this if statement, it evaluates to false because the PID that has been returned to the parent after fork is the PID of the child. It cannot be 0. PID of the child cannot be 0. It's always greater than 0. And what's returned to the child after this is 0. So PID is a variable at this point. Before the fork call, there's only one copy of X and there's only one copy of PID. Okay? After fork, there's one copy of X and PID that the parent sees, and there's one copy of PID and X that the child sees. Now, child sees a return value from fork 0. So child has a PID of 0 stored in its space, and parent has the PID of the child. So will the parent execute these two statements? No, because parent, PID for the parent is something greater than 0. It's the PID of the child, the process ID of the child. This exit will ensure that the child process exits, okay? And parent will keep executing the rest of the statements. So this statement printf, we see X equals 0. So here the child is incrementing X and the parent is decrementing X. We see the child 2, X equals 2, and parent X equals 0. And they will be printed in no particular order. At this point, after the fork system call, we have two logical control flows. And depending on what the operating system does, who gets attention first, one of the processes will execute the printf first, and the other process will execute printf later. So very important to remember, fork is a weird system call. It's a function call that you call once and it returns twice, once to the child and once to the parent. And it returns different values to the child and the parent. So the address spaces are different, but whatever the child had is copied whatever the parent had in the address space is copied for the child. Subsequent changes to X are independent. Anything the work does, the work the child does after fork is different from the parent. Okay, so we can look at process graphs to see what is going on. So process graph is where you start with main. You have the main node, and then at this fork actually means, well, what does it mean? It means forking. It's branch, right? So at this fork, I create a new process, right? And that process will execute all the instructions in program order. It will execute this printf. So this is a child. It executes a printf and executes the exit. We guarded the parent. We don't want to let the parents go where the children are. Okay, we guarded the parent from entering this code block So the parent only executes this printf and this exit. So this is the control flow of the child, and this is the control flow of the parent. So we can create processes now, and we can make those processes do different things. Let's do another example. All right. Can you create? So first of all, how many processes will this code create in total? 4. Can you draw a process graph very quickly? So a process graph looks like this. The main events, you draw them like this, okay? All right, so I think we should just go through this. So the first statement, the parent executes prints L0, and then there is this fork. At this point, there is one other process that executes L1, and then there's another fork that executes by, and all right, let's do it systematically once again. So this is the process. Before any fork, we have the printf. This fork here creates this child that executes the printf. Now it also will execute the by. So it executes the printf L1, then executes fork, and then we have the by from the child process and the by from the original process. And similarly here we have L1 and then the second fork and by. All right. Does this make sense or no? So we have 4 processes. 1, 2, 3, 4. All right. So it's an exercise to look at the process graph and try to see what is happening. So one key idea here is there are certain types of outputs you can expect as legitimate. All right. So this is a legitimate output. This should not happen. You should always go from left to right, okay? So here we are L0. So here we have L0. Does anyone see what the problem is with the invisible output? So you are executing forward in time, then you're coming backward in time, and then, right? This cannot happen on any system. There will be many orderings. The word is ordering. There will be many orderings that look like this. There could be many feasible orderings. Depending on the system, depending on the operating system, depending on what executes first. Once we have 4 processes, they are all fighting for the CPU, fighting for all the resources, screen, everything. So one of them could go ahead before the others. Okay, so what will this do? So this if statement is checking So who will execute this printf? Child or parent? Honestly, I hear two things. Can one of you speak? What, parent or child? Yeah, I'm also confused. Too much teaching today. It's saying is not equal to 0. Who is not equal to 0? Parent, right? Parent gets the process ID of the child, which is greater than 0. Child gets 0. Okay? There's an unambiguous way to distinguish between the parent and the child. What? Huh? The child always gets 0. So parent has a child, it gets a 0. Now, if there's a second fork, this is the parent, this is a child, right? So forget about the grandparents now. Now it's about the, right? So great grandparent, parent, there's always the, you always look, take care of the parent. Forget the grandparent. No, that's a joke. All right, so this statement will be executed by the parent. And then once again, the parent will execute this. Okay. All right. So there's a fork. All right, so why do we have a by here? Why do we have by? Well, a child skips the if statement. Why do we have a by? Yeah, all right. So the child, so this is a parent. Child will skip all this and print by. Now the parent will print L1 and parent does another fork. And once again, the child prints by and the parent prints L2. And finally, the parent also prints by. So visible output, invisible output. Nested forks in children. So this time we turn the tables. When we call for, the child prints, enters, executes these statements, and the parent only execute these statements. So the parent, so the main function starts with L0. There's a fork. The parent goes straight to here. The child is a new process, executes L1, does another fork, parent goes to by, and the child goes to, right, okay. I think that this was a bit confusing, is it? No matter how many times I do it, it will still be. Especially at, I'm looking at my watch, oh my God. Reaping child processes. When process terminates, it is still consuming resources. Various operating system tables, exit status. A process that terminates, we call it zombie. It's still around. It's still consuming some resources. The only time the child is completely outside the system and completely dead is when a parent process reaps the child. So there are different ways of reaping child processes. And once the parent process reaps the child, the kernel in the operating system's kernel then deletes the zombie child process completely. I want to look at the code once again. So this is an example of so we do a fork here. We have the child that exits, and the parent is running in a forever true loop. Okay, so let's see what happens. Now, if a parent does not reap a child, we'll see in a little bit how can the parent process reap a child. It's done through the wait or wait PID system calls. And these system calls make sure that the parent, after creating the child process actually waited for the child process to finish, and then did some whatever the parent wanted to do. It's kind of like when you have a child, you don't just throw them away, right? You watch upon them, you know what they're doing. So even if the child is done with all the work, there is still responsibility. It's still a responsibility of the parent to make sure that the child has terminated properly and to wait on the child and all those things. Okay, so if a parent terminates without reaping a child, then the orphaned child will be reaped by a special process called the init process. We'll talk about the init process in the future, but this is something that the kernel has for bookkeeping and for other things. It's important to reap children because they still consume resources. Okay, so if we have code like that, where we have a child process that hasn't been reaped by the parent, let's see what happens. By the way, I hope you're in the labs, you're at least doing some of the work in a terminal. It will really come handy in the future. So terminal like this, and you type your commands there. So let's look at this example and then we're done. So I'm running this program here. Parent has a PID 6639 and the child 6640. So the child terminated and the parent has no clue. Parent is just running a while one loop. It's very irresponsible parent. It's while one. All right. So PS shows it's a terminal command that prints out on the screen all the currently running processes. And there are different variants of PS. PS is show me all the processes that are running on the system. If we look here, we see that, do you see this? What is this? Which process is this? This is a child process that is defunct, but the parent has forgotten about it. The parent hasn't reaped it. The parent is running in a while loop. He hasn't done anything. So what are we doing here? This is a shell command to kill a process. We are killing the parent process. We are killing the parent. And when we run PS, do we see the child? No, it has been reaped by the init process. Okay, we are done. We'll continue on Thursday.
Yeah, I have this question about the one that we had two four, and when we said we will have four sort of like four branches. Um, how the parents still execute the buy in the first level?